Okay, hello everybody. Welcome to the review session before the final exam of the Physics 121 summer intensive class. It's hard to believe that we've gotten through the month of June. Every time I do this summer class, I think, this is too fast. It's way too fast. But that's what it is. That's what we've all bought into. So we're all done except for the final exam. A couple of things to highlight. The exam is, just in case you weren't clear, the exam is tomorrow. We'll start at 9:30, but it'd be great if you could be there at least 15 minutes early just to make sure your Zoom session is working. It's been pretty good so far, people having, in terms of the technology working out, but I want to make sure that we're there. Just in terms of the way the exam will work, it will be, as I've mentioned before, it'll be a 3-hour block, but we'll break the exam. I won't just give you the whole exam and give you 3 hours. I will give it to you in 1-hour chunks. I apologize for those of you who want to hurry up and go, but that's the format that we have to work in, given the technical constraints that we're under. So it'll be an hour, it'll be 50 minutes with 2 questions, and you send it back. 50 minutes again, you submit another file. The Canvas will let you submit multiple files to the final exam assignment. So you just keep submitting new versions of that, new files until we get all 3 files. One thing I'm doing a little differently this time is I'm asking you to submit your 5 pages of crib, up to 5 pages front and back of crib sheets, and I'm asking you to submit those before you start the exam instead of with your exam. Several students were a little vague about whether they had crib sheets or not. So some of you regularly submitted your crib sheets. Sometimes I didn't see those crib sheets. So to make sure that I get a chance to see your crib sheets, I'm giving you 10 bonus points. I put an assignment up, 10 bonus points, 3 points. All you have to do is send me your crib sheets before the exam starts. And I have a special assignment slot for you to do that. You can do that anytime you want between now and 9:15 tomorrow morning. But to emphasize, that's anything you want that you're going to want to actually look at during the exam has to be on one of these 5 pages. It's front and back. So you actually have 10 sheets of blank paper to put things on. And again, I'm not going to grade them. I'm not going to, as long as you've written something down that's plausibly helpful for doing an exam. I mean, don't just, scribble and write cartoons. As long as it's plausibly helpful, I'll give you the 10 bonus points. Otherwise, it's a closed book exam. So just to make that clear, you can't print out solutions from the homeworks and have them sitting next to you or on the computer. You can't look at old exam questions. You can't have any of that stuff up in front of you on the computer or on your thing, just so you know it. Everything that you would be able to look at needs to be in these 5 pages. It could be anything you want. You could take an old exam problem, work it out on one of the pages and include that in your crib sheet. That's perfectly fine. Then you can look at it. But then I know that's what you're looking at. That's the point. I want to see what you're seeing. That's the whole idea. So, and then the other thing to highlight is how the exam will be graded. And I think people have gotten the idea, but I want to emphasize it one more time, especially for the final. The way we grade physics problems in this class is we don't just look at the answer and say, oh, you got it right, and give you all the points and 0 if you don't. The way we get through a physics exam in a course like this is through the miracle of partial credit. And the only way that you're going to get partial credit if you don't have the exact right answer at the end is if you show us how you got there. It's the method that's important, not the result, at least for introductory physics. And so the grading will reflect that. So at least 25%, at least a quarter of the points you can get by simply identifying the main concept. So there's a lot of main concepts, and we'll go through a concept map to sort of talk about them. But I don't need a paragraph. I don't need a long explanation. I just need sometimes it can just be a simple acronym. I need you to tell me where it is in the conceptual universe of problems you are working. And you can't skip this. If you look at your answer and all you see is algebra and no words at the top of the problem saying, this is what I'm going to do, then you haven't identified the main concept. You get at least a quarter of the points and maybe even a third of the points just for setting up the problem. So what do I mean by set up? I mean, draw a sketch, identify the given parameters, figure out what the initial variables are, and write down the key equations and how those variables fall into those key equations that will set you up working on the problem. So for a Newton's law problem, that would include a free body diagram, and it might include, F equals ma is written out for each of the particular components. And if you just set it out, or for conservation law problem, you should make it clear what the before and the after is, which variables apply to where. Again, you don't need to solve it, you just set it up. If you set it up, if you identify the main concept and you set it up, you're guaranteed to get half the points if you do it correctly, even if you never solve the problem. And if you do it well, I may give you more than half the points, right? And then finally, at least a third, but up to a half, is your actual technical solution to the problem. And actually more important, I mean, if you make an algebra mistake, you will lose points, but more important than algebra is coherence and organization. Make it clear to the grader, that's me, what you're doing and why you're doing it. And, if something, if you make a mistake and you don't want something to be graded, put an X through it, make it clear, oh no, that's not what I want to do. Write some notes or draw some arrows so I can follow the logical flow of what you're doing. That's part of the answer too. And when you get to the end, please put a box around your final answer. That's really helpful. And then you're all set. And I would say solve symbolically, not numerically, but almost certainly all of the problems will be symbolic, not numerical. Okay. So anybody have any questions about the exam, how it will be organized, what the structure will be in terms of what to expect? I mean, it should look like 3 versions of an hour exam done together, but covering all of the course of the material. And again, if you take the time to turn in your crib sheet before the start of the exam, I'll give you 3 bonus points. That means 10 bonus points. That means I'll kick your final exam score up by 10 points before you do the grading. For free. All right. So we're going to do 2 things today in the review. One is going to sort of put out a concept map there and maybe talk through 1 or 2 examples of how this conceptual map works. This is a way of thinking about how to tackle problems, especially on a final exam, where you're not really sure which concept to use. It's the most important thing. I mean, how could I put it? If I give you a problem where the only way to solve it is to apply, say, the work energy theorem, I mean, you do something else like Newton's laws, you've identified the wrong concept, everything that follows will be a disaster. The only way to do well in the problem is to identify the main concept. It's the most important thing. So how do we do that? So one way I like to think about it is I like to think about it again in terms of a conceptual map. So I've drawn this before, but let's actually sort of spell out what we've gotten to in the whole course. So this is the study of motion. It's called mechanics. Motion we're going to divide into 2 main ideas. Oops, it would help if I actually do the right one. Hold on just a second. So kinematics and dynamics. So there's a couple of things that are important about this conceptual map. The first is it basically redefines. I mean, physics isn't just a bunch of equations and plugging things in. Physics is a set of concepts that you apply to solve certain kinds of problems. And what our objective for the semester is to see to help you understand those concepts, and our assessment is to determine whether you understand those concepts by asking you to solve problems where your understanding is demonstrated. So every problem I give you is designed to see if you understand the concept. That's why I've written it, okay? So kinematics, the key issue for kinematics is it answers the question how, and dynamics answers the question why. So in other words, kinematics is a description of the motion, and dynamics is basically a discussion of the causes of the motion and what the consequences of those causes are. So what falls into kinematics? So we've dealt with kinematics. And I'm going to make a fork here. In some sense, where there's lots of ways I can do this. This is not the only way to make a concept map for the course, but it's at least one way that I like to organize it in sort of this tree branch way. One way is in the concept of what we would call translational motion, translational or linear motion. And that basically breaks down into 1D motion. So we have things like X and V and A and constant acceleration, things like this. And then 2D kinematics, or typically 2D, but sometimes in principle 3D. And that includes things like uniform circular motion, projectile motion, projectile, I'll put that there, I hats, J hats, and sometimes K hats, tangential and centripetal acceleration. Problems like the orbital path or the spirograph. All of this, kind of packing it in small, sorry. All of this corresponds to linear motion, translational motion kinematics. Position, velocity, acceleration. And the usual way to answer the question, do I need to use this kind of kinematics, is to answer the question, am I given the position as a function of time? Or am I told there's a constraint about the motion? Is the motion in a circle? Is the motion a projectile? Am I given asked for these Cartesian unit vectors, tangential, etc. And then there's another component of kinematics, which we call rotational, which we dealt with at the end, otherwise sometimes also known as angular. And at least in terms of X, V, A, and so forth, we have the analogous quantities of theta, omega, alpha, and rules for constant acceleration. Okay, so not too many, lots and lots of problems fall into this category. And on occasion, you just use analogy to do this kind of equation. So the problem with the bicycle wheel, or trying to figure out how long it takes the space station to stop on a homework problem, that would be an example of applying rotational and angular kinematics. Okay. But sometimes we do dynamics, and the dynamics, again, there's two main forks. The first fork is what we call Newton's laws. And Newton's laws basically also forks into essentially the rules for linear motion, so translational motion, where we have F equals ma, free body diagrams, Newton's third law, etc. All of this, the recipe. Okay. And then now in the second part of the course, we have rotational dynamics for Newton's laws, where we have now the rotational form of Newton's laws, tau equals IA. We have extended free body diagrams, and we have so forth and so on. And we have the definition of torque. Tau sub F equals R F sine phi. All of these details go here. Okay. And then finally, on this side, we have conservation laws. Conservation laws. and they fall into two main branches. One is conservation of mechanical energy, and the other is conservation of, and then we have basically a fork, linear momentum and angular momentum. Okay, so there's essentially three different conservation laws, these three, and sometimes we apply those. A key concept for conservation laws is that we have to have a before and an after. And another key concept of conservation laws is that there's a condition. And on the last exam, some of you, how can I put it? The third exam, you got the conditions a little mixed up. So be sure somewhere on your crib sheet, somewhere between now and tomorrow morning, if you're not absolutely clear what the conditions are for conservation of mechanical energy, write it down on your crib sheet and check it as you're doing the problem. The condition for conservation of mechanical energy is the condition of that the forces are either conservative or do zero work. And the conditions for momentum is that the system is isolated. In other words, either zero net torque, zero net force, or zero net torque. Right? And by the way, these things in particular are important for collisions. And again, make sure you can, so we're start tying these together, make sure you know the difference between an elastic collision, where the kinetic energy is conserved, and an inelastic collision. Okay, because again, a couple of you got that mixed up last time. And once you've got all of this, there's a couple of bridge concepts that basically live between these two things. One of them, and I'm kind of out of room, so I'm going to kind of write it small, but and off to the side. So one of them is the classical work energy theorem. So this is a bridge concept. Right, and that basically says that the total work done is equal to delta K, the change in kinetic energy. And another thing that, so again, that lives in between these is, and I'm squeezing it in here because I don't quite have enough room, is the impulse and momentum. Impulse-momentum relation. So I would say for most problems, well, so again, where in this sea of stuff should you study, right? I mean, it's getting crowded and big, and if we go into these details, you can make. I've made concept maps that have like another, 20 sub branches. It's a lot of material we've covered, and somewhere in this regime is, for example, the different forces. Somewhere in Newton's laws of the force mass menu, all the different forces, universal gravity, so forth, spring force, and then of course once you got the spring force, you got oscillators, all these things. Oscillators have force and energy, so there's these crisscrosses, all of these things. But this is the main idea. So what's our approach? So the good news is that the vast majority of the problems that you will be asked to do fall into these branches, right? Which is to say, the key ideas for the courses are Newton's laws, especially in the linear form, but now towards the end, there's going to be maybe one or two questions on the exam for rotation. So you got to have that. And the other key idea is conservation laws, especially mechanical energy and linear momentum. So it's been a couple classes, but also possibly angular momentum. And in particular, you should be able to deal with collisions. Okay, those are the most common things. On occasion, as you're working through one of these problems, you might be asked to jump over to apply kinematics, or you might be given a simple question that is just on kinematics. So on the practice exam, the first problem I give you is a kinematics problem. So is the problem. There are a couple problems with projectile motion. Those are kinematics too. But even though they're on the practice exam, they're not going to be the most important thing. The most important thing is Newton's laws. I guarantee you there will be a simple, straightforward Newton's laws problem on tomorrow's exam, in the sense, simple and straightforward in the sense that it will be a problem that you could have solved during the second hour exam. But I also guarantee you there'll be at least 1 or 2 problems where you have to use conservation laws, and you have to check to see whether you meet the conditions. And then, if all else fails and you're working through a problem and you're really not sure if one of these main ideas is going to work, then there's some possibility that I will pitch a bridge concept problem at you, most likely conservation, the classical work energy theorem, W total = delta K. Less likely impulse momentum. I've given you 1 or 2 problems on that, but that's not my favorite thing. So why have I gone through this exercise? I've gone through this exercise because if you have this mental map in your mind, or you've written it on your crib sheet, you can think about how you're going to tackle certain kinds of problems. So, for example, let me see if I can find that. So, for example, if you probably don't have it in front of you now, but that's okay. But there's a problem. The second problem, I'll just give that as an example. The second problem has a car going up a hill. So I'm just going to write it in the corner here. I'm not going to work through the problem. The solution's already there. But there's a car, and it goes up the hill with some radius of curvature, and then it goes back down. And so I ask you a bunch of questions. This is an example of a kind of a typical compound problem. And so the first question I ask you is, assuming that the cart is rolling without friction and there's, it's coasting, what's the speed when you come up here? So I give you the initial speed and I give you the final speed. Anytime I ask you for speed, you should think, oh, wait, okay. So if I'm asking for speed, you might think, oh, translation, no. Again, the key issue for kinematics is I need to be giving you the position as a function of time, or you need to know that the acceleration is constant. That's not happening here. But here, if I'm asking you for speed, you should always be thinking, oh, I've got a before and after. Can I use conservation mechanical energy? Because there's always, kinetic energy has always got a speed in it. So that's where you should think. And then once you convince yourself that the forces are conservative or do no work because you're rolling along and the only force is normal force and weight, then you can use it. That's great. And then the second part asks you to calculate the normal force on that car. And the key thing then is to recognize, oh, I'm on a curved surface. So if I'm on a curved surface, that means that I've got basically centripetal acceleration, and the component of the force is centripetal. So I just apply Newton's laws down this line where A is equal to AC, which I know. So anytime you're on a circular path or you know the acceleration is constant and you're asked about a force, you can work your way down this path. And that's going to be perfectly fair game for this kind of exam. And then I ask you some kind of tricky questions about going from here to here, where the brakes are applied, right? And it gets complicated because if the brakes are applied, then you go down this way and you say, I don't know what the force of friction is, so I can't solve this problem this way. And if the brakes are applied, you try to go to conservation of mechanical energy like you did in the first part, and that doesn't work. And so your only hope, having gone down these main branches, is to try classical work energy theorem, and it works, okay? So again, this idea of like, start where you're most familiar, Newton's laws, conservation laws, occasionally jumping here, and then try the trees out, and if you go down the branches and it doesn't work out, try another branch, like the bridge concept. If you try conservation of mechanical energy and linear momentum and it doesn't work, then finally try angular momentum, right? Especially if something's spinning, right? And then, try to keep track of what you're doing. So that's my overall strategy. And if you're not sure, how can I put it? This is my advice. If you're not sure that you're using the right concept, it's worth taking them 30 seconds and a minute to write out at the beginning of the problem, I'm going to try this concept. I'm not sure it's the right one, but this is what I think. You're asking for speed, and it looks like a collision, so I'm going to assume that this looks like an elastic collision. And maybe your guess isn't wrong. Maybe you've chosen the wrong concept, but at least you've told me what you're thinking. And I can give you partial credit for trying to solve the problem in the framework of whatever concept you're actually using. If you simply just start in without telling me, oh, maybe this isn't right, or you don't just give me some equations and you don't tell me where you are on this map, then I'm going to assume that you don't have any idea what you're doing, and it'll be really hard for me to find partial credit. Explain your work, explain your thinking, especially in the concept of, in the regime of all these concepts. Which concept are you trying to apply? And don't just throw equations in. Tell me what you're thinking. So, and again, I don't need a paragraph, just a few words or sentence. You know, F equals, you know, Newton's second law, N2L. You know, C of ME, whatever you're using, and then maybe, you know, again, be sure you check those conditions. Okay, that's my general advice for the exam. Any questions about that? Any questions about any material that you're worried about, any topic that I haven't covered? I will remind you that this week we looked at gyroscopes, oscillators, waves, static friction, and using the coefficient. And we talked yesterday about non-inertial reference frames and the gravity. Question of, is that material going to be on tomorrow's exam? The answer is, at most, one of the 6 problems will have something to do with one of those topics. So more important that you master this, and then if you got some extra time to review the stuff we did the last 2 days, that's gravy too. But you know, I could put something on there, but I won't put more than one question on for those topics. Much more likely that this space will be evenly sampled for 5 or more of the problems. Okay. So at this point, what we're going to do is I've got some they're kind of like, what we call them clicker questions. They're basically simple questions that have multiple choice answers that you can answer, and they've been designed to test your understanding of concepts. I don't know how long it'll take us to go through it, but probably about a half an hour, which is what we have. There's maybe a dozen of them or so that we'll go through. They cover all kinds of topics. Interestingly, a little bit more kinematics on this side than the rotation on that side, but there's a mix. You never know. And it's a good way to sort of check your understanding. So if you're on the Zoom, the way we're going to do this is I'm going to post the question, and then I'm going to start a poll. And the idea is that you get to vote on the poll. Vote for your answer near a poll. Again, I won't grade this. It's just an exercise to sort of check to see where you are. Oh, and by the way, for those of you who are watching this after the fact, or if you're concerned about it, your participation will not be graded. I'm not keeping track of your answers. I don't care whether you're right or wrong. All this is just a way of what's nice about the polling is that you get a chance to see how your understanding compares to other people in the class. All right, so how am I going to do this? I'm going to share my speed. First of all, I'm going to share my screen. Let me make sure I've got the file up here. That's the one I want. All right, let's get rid of, give me just a second to set this up. Okay. So I'm going to share my screen. That one. Share. All right. Can everybody see that? Let me know. Can somebody let me know if you can?
Yeah, we can see it. Great.
So now you see a question. The ball is thrown straight into the air. What happens at the highest point? You get 5 choices, and if life is good, you should be able to answer that choice A, B, C, or D, or E. And once you've read the problem and you think you have an answer, just make your best guess. All right, I'll give you a few more seconds. Okay, let's see if I can do this right here. So I'm going to say call an end here, end polling. I'm going to stop the sharing for just a second so I can talk about it. So you can see what the results are. Most people pick C, but a few people picked A and B. So I'm going to demonstrate the problem. So if I go like this and stand here, and I toss this up, whoop, whoop, I'm talking about right at the top. Okay, so first of all, conceptual map. What kind of problem is this? This is a problem I'm asking about accelerations and velocities, so it's a kinematics problem. In particular, it's free fall kinematics. So it's all the way back to the beginning of the class. And in free fall kinematics, you should have this mental map that the acceleration in the y direction is equal to negative g. It has some value. And the velocity is equal to some equation. But the velocity right at the top, as I go from the turnaround from going from here to here, the velocity is instantaneously equal to 0. So the right answer is, even though we're at the top and the object is momentarily at rest, neither going up nor going down, therefore its speed is 0. Nonetheless, it is still in free fall. There's nothing touching it, at least in the, I'm touching it now, but let me do the problem. It goes up. It's still in free fall, which means that even though it's transitioning from going up to going down, it's still accelerating, which is to say it has a constant value of acceleration. So the right choice is choice. Let's see if I can go back to this. Stop share, and we will go, I can do this, it's exactly right. Here we are. So the right choice here, the other way. So the acceleration, so wait a minute. So the acceleration is non-zero, which is to say g, but the velocity is 0. So yes, happily that's the right answer. Okay, cool. So if you got tripped up on that, let me know. I mean, don't let me know, just think about it for a second. Make sure you got clarity in there. Let's do another one. This one's relatively simple, so I'll give you a short period of time to answer this question. So I've got a plot of x versus t, and I describe a story of a jogger stopping to tie his shoe and then carrying on. And I want to know which of those maps corresponds to reality. So take your best, which timeline. So vote your favorite thing. All right, I'll give you a couple more seconds to vote. Again, I'm not keeping track of who's voting what, so there's no reason to worry about. Just take a best guess, see what we got. Okay, I'll stop vote now. Okay, so you can see people are voting all over the place. Most of you have come in at C, but there's some other choices. So let me reflect a little bit about these choices here. What we're talking about is position as a function of time. So it's kind of interesting to think a little bit about the maps that correspond to A, B, and E, because they have vertical lines in them. And a vertical line means that basically the position of the body has changed from one point to another point without any time going forward. So the way I like to put it is that the plots corresponding to A, B, and E are, how can I say it? That corresponds to teleportation. That corresponds to the jogger disappearing from one location and reappearing in another location. That's not physically possible. In other words, we don't expect a discontinuity in X versus T. So we can rule out A, B, and E. So that leaves C and D. And then the question is, which of those makes more sense? And in this case, he says he stops to tie his shoe. So the key issue here is what? Is how do we get velocity from a position versus time curve? We look at what? Anybody? What do we need to look at to get the velocity?
The slope.
The slope, that's right. So, and in this case, the jogger Stopping means the slope ought to be 0, which C and D both have. But we're told that the jogger speeds up instead of slows down. So in other words, the slope increases after stopping, which is the case in C. So C is the right answer in this case. Okay, let's go to the next one. By the way, I'm going to post all of these on the website so you can review them in your own time, along with the solutions. Okay, this one's kind of cute. I've got a body moving in a 1D world line as shown. So I've got, again, X versus T. And I want to know which of the following 5 options is true. And the body might be moving with constant velocity. The body speeds up for a while and then slows down. The body is always speeding up. The body's always slowing down, or none of these is true. Take your best shot. See if you can sort it out. These are a little tricky. They're simple questions, and yet they check your understanding. What I tell students is that these are good diagnostics for what you understand at the surface level, but perhaps what you haven't quite understood at a deep level. Not a cause for panic, but it's worth checking yourself at this point. So let's see what we got. Okay. So you can see there's a mix of answers here. Now, we had a little more time, which we're running a little tight on. And if we were in a physical classroom, I would ask students to pair up and try to work out in teams which of those answers are best. But let's see if we can kind of work through it here. Just a second. So let me stop the sharing for a second. So we can kind of consider the problems. There's the problem here. This is X, and this is T. So again, I like to ask students to kind of make a mental, what's the movie of this motion looks like. So this is position as a function of time. And then I can say, well, what does the speed or the velocity look like as a function of time, right? I'm asking you for speeding up and slowing down, okay? So speeding up corresponds to the velocity getting larger. Slowing down corresponds to the velocity getting smaller. We all agree on that? So in this case, I say, well, how am I going to infer the velocity? I've got a slope. So here the slope is high, and then here the slope is not as high, and here the slope is not as high, and here the slope is getting even less and slowly getting towards 0. So without actually knowing exactly what the shape of this is, I can say, well, at low times, the velocity is high, and then as time goes on, it basically goes down like this. So even though you start fast and end up slow, you're not actually speeding up here. You're not you don't conflate the increase in position with the decrease in velocity. Okay? So the right answer in this case is that I'm always slowing down. Okay, so if that got you fooled, think about it for a bit and make sure you're on track. Okay, so I like this problem. This is a key problem. We launched the poll. You can see I'm not keeping your answers or anything. I'm just starting the same poll over and over again. So you're inside an elevator. Everybody can see that, hopefully?
No, you're not sharing.
No, I got to share it. Hold on. Thanks. Share screen, that one. Share. Now you can see it. Hopefully you can see that. You can see the poll too, yes? Can you still see the poll? Hopefully. All right, so you're in an elevator. you're moving with constant, the elevator is moving up with constant velocity. I'm giving you the mass of you, the mass of the elevator, the tension on the rope, all this fun stuff. And I want to know, what is the magnitude of the net force on your body as a consequence of your motion inside the elevator? And your choices are mg, vt plus a constant, exactly 0, t minus mg, well, there's some fun expression there, t minus mg, or something else. Could be none of those four things might be, it's possible that none of those four things is the right answer. And it's problems like this that make the students really complain. They're not happy. Not happy with me, because I'm much too sneaky. All right, let's see what we've got. Again, all over the map. Ignore the colors on the bars. I have no idea what those mean. I guess they're the most voted. All right, look, let me ask you this question. Which body are we talking about? We're talking about you. We're talking about that little green person sitting in the box. Does the tension force apply to you? Is it physically, is there a rope physically connected to you? No, there's no tension force applied to you. So that's tension. Not obvious if the tension force has anything to do with anything. The tension force is applied to the elevator, and there's obviously going to be some normal force applied to you from the elevator, and the value of that normal force could depend in principle on any of these other variables. But just go back. By the way, what's my favorite law of physics of all time? What's the answer to that question?
Newton's second law.
Newton's second law, right, exactly. So I'm asking you, what am I asking you? I'm asking you for the magnitude of the net force. So if I ask you for the net force, ignore everything else and simply ask yourself, do you know the acceleration? That's the whole idea. I promise you I will ask an exam question like this. So by the way, what is your acceleration? Because you're moving with constant velocity, your acceleration is?
0.
Is 0, so the net force on you is 0. Stop. It's exactly 0. C. So almost everybody missed it. If you missed it, say, oh yeah, okay, so I fooled you, I'm evil. By definition, yes. I deliberately set you up with all this extraneous information like tension and masses and all this stuff. And none of that matters because the net force is simply ma, and a is 0. Start with Newton's second law. Ask yourself, if I ever ask you for the net force, ask yourself, so don't try to add up all the forces. Simply start by saying, do I know the acceleration? Because that's what I'm looking for. Okay? Let's do another problem. This one's a little harder. A speeder, in other words, somebody driving a car who's going too fast. That's what I mean by a speeder. A speeder is going down the road and notices ahead of him a sitting police car. The speeder slows down, but it doesn't work. The police car pulls out into the road and pulls the speeder over. Which of these plots describes the acceleration of both cars during the event? So here, to be clear, I'm not plotting position as a function of time. I'm plotting acceleration as a function of time. So see, again, there's a movie going on here. Two cars, or a car and a motorcycle, whatever you want to say. And one of those objects is green and the other is blue, and you're looking at the acceleration as a function of time. I'm asking you to figure out for sure which one it is. That's just only one of them is plausible, and the others are not. And again, I'm plotting acceleration. This one's tricky. This one's hard. Because we're used to thinking about position and velocity, but we're not used to thinking about acceleration. All right, let's see. Anybody else got a vote? It's all over the map. People, I like it when people change their votes. It's kind of fun for me to see. I know you can't see it, but I can see it. All right, let's see what we've got. All right, so again, the results are all over the map, but it looks like the favorite is C. So if you look at C, you look at the blue line, and it starts off high, and then it gets slower, and then it gets lower, and then it goes all down to 0. And if you look at the green line, it starts off 0, and then goes up to some positive value, but then it gets down, go back down to 0. This is a very nice plot, and it does describe the motion, but it does not describe the acceleration. What does it describe? It's not the acceleration that's being described here. Some other quantity that's being described. Not the acceleration, but anybody? Can you think about it for a second?
Velocity.
The velocity, yeah. In other words, the speeder starts with a high velocity, taps on the brakes, goes to a lower velocity, and then the police car pulls out, and the speeder slows down to 0, and the police car speeds up, catches up, and then slows down to 0 too. So C is a description of the motion, but it's velocity, not acceleration. Acceleration corresponds to changing the velocity. So if you change the velocity, that means you either have to hit the brake or hit the accelerator to change your speed. By the way, notice that A, B, and D end with non-zero accelerations. In other words, in A, B, and D, the final result is that the acceleration is more than 0. And if the two cars end up at rest, then by definition, that can't be right. So what's left is E. And E makes sense. If you look at E, just stare at E for a second and think about the movie. So put it this way, does the speeder ever speed up? Does the speeder ever increase his velocity? No, because if you're driving past the speed trap and you slow down, you don't speed up. The last thing you do is speed up. So the speeder's motion, the speeder always slows down. So that's accelerate. That's the blue curve, deceleration. The speeder taps on the brakes, coasts for a little while, and then taps on the brakes again and finally comes to a stop. In contrast, the policeman who's giving the ticket starts off at 0 acceleration, then accelerates to catch up with the car, and then decelerates to stop. So that one's a little tricky. But you should, the whole idea is that you want to build up a conceptual map in your head of what's going on with each of these quantities. Okay. So let's go to the next one. Doing pretty good here. All right. I'm not going to say anything. I'm just going to relaunch this poll, and I'm going to let you work on this particular problem. This looks kind of familiar, but it's different. So take your best guess. So again, the net force, I'm asking the question, what is the net force on your body? Its magnitude and direction. Okay, we'll call that good enough. All right, so I don't know whether you should be comforted by the fact that whatever you've done, there's a lot of confusion, and so you're not alone in that confusion, or terrified by the fact that such confusion reigns. So let's try again. Let's take a deep breath. Okay, so fool me once, shame on me. I fooled you once. Now fool you twice, shame on you, because you've been prepared and yet you still fell into the trap, or at least most of you did. Look, there's all this kind of stuff going on, but what have I asked you? Have I asked you to calculate the normal force? I think a lot of you are trying to calculate the normal force here. If you ask the question, what is the normal force, then some of those answers are not so wrong. Or well, they are wrong, but they're not, at least they're heading in the right direction. But I have not asked you for the normal force. I have not asked you to tabulate all the forces and add them up. What have I asked you for? I've asked you for the net force. What is my favorite equation? Again, what is my favorite equation in all of physics? Newton's second law. So I've asked you for the net force. So that means all I'm asking you for is the mass times the acceleration. What is the acceleration of your body in this problem? It's A. It's given. It's A downward, capital A downward. So your acceleration is A downward, and therefore the mass times acceleration is MA downward, and that is the net force. So congratulations to the three of you who actually got the right answer for part this and chose part A. But if you didn't, you've been fooled twice. And I'm warning you, I'm telling you now, I'm going to try it again. I'm going to try to catch you off guard one more time. I'm going to catch you off guard in this sequence of questions. I'm going to try to catch you off guard on the exam tomorrow. So don't be off guard. If I ask you for the net force, what do you look for? The mass times acceleration. That is Newton's second law. Okay? Anyone have any questions about this? All right. Okay, here's another question. A ball is attached to a string. Oh, man. And it's swung around in a vertical path, so it moves with given speed v on a circular path with radius r at the top of the path. So you know the speed of the ball. You know the ball is at the top of the path on vertical path, so gravity is pointing down in this picture. And I'm asking you, what is the net force on the ball at the top of the path? And those are all your choices. Okay, I'll give you another minute or so, a few seconds. Okay. So the good news is, by the way, again, if you're freaking out, don't freak out, because this is, I do this every time. It always happens the same way. It takes a while, but by the time I ask the same question the third time, most people get it right. Not everybody, but most people get it right. They say, oh, he's asking for the net force. He wants the mass times the acceleration. The mass is down, the acceleration is, well, if I'm moving on a circular path, the acceleration is, by definition, centripetal, which is to say towards the center of the circle, which is downward. So the right answer is, here we are, B, downward. Okay, so you're ready for the exam tomorrow. I may ask, in fact, I will ask a similar kind of question tomorrow. And if you try to give me a free body diagram and you try to give me all kinds of other stuff, instead of simply saying MA where A is known, you'll be in trouble. All right, let's do something different. Here's a quick one. A bug is flying down the road and collides with an oncoming truck. Splat. Which feels more force during the collision? A, the truck. B, the bug. C, the bug and the truck feel the same force, and D, none of the above. I don't see how D is logically consistent with anything, but tell me what you think. Which feels more force? So again, every one of these problems is designed to understand, is designed to check to see if you understand at a reasonably deep level, not a technical level, but a conceptually deep level, some major concept. So ask yourself, which major concept applies here? If you can't find a concept to answer your question, then you're probably not, then you probably aren't getting the right answer. You're probably, you need to grasp and show us that you've understood the concept. That's the idea. Okay, so let's see what we got here. All right, so some variety, but most people converged on C. So what is the main concept that applies here? That's the question. What is the main concept?
Newton's third law.
Newton's third law, right. So remember, Newton's third law is powerful but dangerous. You only bring it out on an occasional basis, and the time when you bring it out is when you have two bodies interacting and you're interested in both of the forces. So that's exactly what's going on here. I've got a force of the bug on the truck, and I've got a force of the truck on the bug. And by definition, Newton's third law says that the bug and the truck will feel the same force. Now you may say, obviously the consequence of that force is different for the bug and the truck in the sense that the bug gets splatted and the truck does not. But that's because the bug has a tiny little mass and therefore it experiences a violent acceleration, whereas the truck being much heavier just carries on to slow down a tiny fractional amount, but it hardly notices it. But it's still the same force, right? A bug and a truck will both feel the same force by Newton's third law. Okay, got a couple more. We're almost done. All right, so this one's a little more technical. Let's see if we can work it out. So we're on an oval track. So the car is represented by the point, which is on the oval track at the top. So this is kind of like a bird's eye view of an oval track, and the car is going around the track in a counterclockwise direction, so that at this instant it's going in the negative x direction, corresponding to these coordinates. And also the car is slowing down, which is to say its speed is decreasing. And so I want to know, well, if P and Q are positive constants, we don't know what they are, but they're positive, and we're defining the vector corresponding to the acceleration of the car, which of those expressions is the right expression for the car? In other words, I expect figure out which way A points. A could point either positive or negative in the I hat direction, and the acceleration could point positive or negative in the J hat direction. And one of those sets of choices corresponds to the right thing, but others don't. And this is important. I'm not asking you for the magnitude of the acceleration. I'm asking you for the vector expression that corresponds to the acceleration. I think I've got one more after this, so I'm sorry to run over. I'm running a little over, but I think I will do one more after this one. So let's see what we got. We got some reasonable sense of the voting here. Most people picked B, which corresponds to positive, negative. All right, and so let's think about this for a second. So I'm going to switch off of sharing for just a second so that I can show you what I got here on the board. So here's the particle, and that's the velocity. That's x, and that's y. So let's do the easy part first, the vertical part. So I'm on a curved surface, So that means there has to be centripetal acceleration. So there must be a component of the acceleration downward towards the center of the circle because I'm curved this way. So that means that in terms of j hat, that's pointing to negative. So that means there's got to be a minus q j hat. That part's easy. And then trickier, considerably trickier, is the fact that I'm slowing down. Well, I'm slowing down, but I'm already moving in the negative x direction. So that means my velocity is becoming less negative. So the change in velocity is in the positive direction. So it's plus p, positive p I hat minus j hat. Ooh, tricky. And if you got that, good for you. You've got your I hats and j hats in good shape. That's a tricky problem. All right, I think I got one more for today. Let's go back to share screen. All right, so just as I've drawn there, we'll skip that one. I'll post it, but we'll skip it. Let's do this one. This one only has 4 choices, so it can't be too hard. Relaunch. So don't choose choice E because it's the wrong one. So you're standing on a frictionless cart, which is to say you've got little wheels on there, but I'm going to ignore the wheels. All the wheels are doing is basically getting rid of friction. The tiny little wheels that basically give you no friction between the cart. But the cart itself that you're standing on has friction, and you're standing on the cart. You don't slip or slide. You're on the cart. And you've got a ball, a rubber ball, and you throw it. And for odd reasons, we've put a plank or a board mounted firmly to the left-hand side of the board so that the ball bounces off the board and then goes shooting out over your ear behind you. And as a result of having done this exercise, I want to know which way is the cart moving after the ball rebounds off the wall. And your choice is the cart moves to the right, the cart moves to the left, the cart will be at rest, or it depends on the mass of the ball, the mass of the cart, and thrown velocity. And let me tell you one other thing. Obviously, this collision is not totally inelastic. Well, not obviously, but it can't be totally inelastic, the collision between the ball and the board, because it would stick if it was totally inelastic. But you're not told, in contrast, that it's totally elastic. You don't know that either. It could be elastic, but it might not be totally elastic. It might be partly elastic. You don't know. It's some collision, and as a result of the collision, it doesn't stick, but you don't know other than that what kind of collision it is. All right, so let's see what we've got. All right, so again, this is a tricky one. We've got answers all over the map. So now, for those of you who are, anybody of you who are brave, again, I don't know who you are, so you can speak up and I won't hold you against you. What is, anybody who feel like volunteering, what is the main concept that applies to this problem? That's the question. What is the main concept that applies to this problem?
Conservation of momentum.
Conservation, so we got one vote for conservation of momentum. Why does conservation, so I like that vote. Can somebody else tell me why that might be a good thing? What would be the advantage of using conservation of linear momentum here? Why would that be appealing? Why can we, what lets us know, what tells us that at least it's an option?
There's a before and after.
So there's a before and after, that's good. What about the condition? What's the condition? Every conservation law has a condition. What's the condition here, and does it apply? Anybody? So what is the condition?
If it's isolated.
It's isolated, right. So that means there has to be no net force on the system. And of course, the thing is, what's the system? So obviously, you, the ball thrower, that's not the system. You're not isolated. You're applying a force to the ball that goes flying off, and also there's a force of friction between you and the cart. But if you make the system everything, the ball before you throw it, and you, and the cart, then, well, the vertical, again, we're ignoring the vertical forces here. It doesn't matter whether the ball falls up or down. All it matters is the horizontal motion. And horizontally, there are no forces on the cart at all. Well, there's a force between you and the cart, but that's an internal force. And there's a force between the ball and the board, which is attached to the cart, but again, that's an internal force. The key to this problem is saying, I define the system as everything I see, the ball, the person, the cart, the board, the wheels, everything, except the floor, of course. And that system is isolated. There's no, for the whole problem, there's no net force on it. Even as the cart might move, there's no friction, so there's no force on it. So you start at rest. You got the ball in your hand, you're about to throw. What is the total momentum of the system?
Zero.
It's zero. That's the whole key of this problem, is to recognize that we start with zero momentum. And therefore, we must end with zero momentum, because conservation of momentum. That means if the ball is flying over your ear to the right, the rest of the system must continue somehow to the left, right? That's the idea. All right, so that's all I've got for today. That's my review. Again, you got to figure out for every problem. So even though these are conceptual problems, the same kind of approach applies here. You've got to start with the right concept. Let me know, the grader, what concept you're using, and then see how far you can get using that concept. Okay? If you're using a conservation law, be sure to tell me what to demonstrate that you've met the conditions. If you're applying Newton's laws, be sure to make the steps in the recipe clear. Always start with the acceleration, because F equals ma. That's my favorite rule. Start with that, and then tell us whether you know about the acceleration, so you don't lose track of it. And then explain your work as you go. Don't just put the equations and the answers. Be sure you have at least a few words here and there telling me what you're going to do. All right, that's all I've got for today. I'll stop sharing. If anybody has any questions, I will have office hours as usual at 4:30 today, but if that time doesn't work and you want to meet with me some other time this afternoon or evening, just send me an email and I'd be happy to meet with you. Yeah, take the time to work through those practice questions and look at the practice homeworks. Take a little bit of time to make sure you've got your crib sheets all together, and please submit those crib sheets before we start tomorrow morning. That's it. If you have any other questions or concerns? Any questions? Anything you want? Anything you want to toss at me? Otherwise, good luck with studying, and we'll see you tomorrow.